In this video, we are going to talk all about nuclear reactions. And the key to understanding nuclear reactions is looking at how things decay. And remember, to decay means that it's going to break apart. Okay? So if we have things that are breaking apart, we are going to see things in multiple pieces. Okay, so when a reaction is going to occur, it's basically when an unstable atom loses energy. That's going to emit some of that radiation. It's spontaneous, it requires no energy, just there are these unstable isotopes. But one of the key crucial parts to remembering how to do these nuclear reactions is that it always has to obey the law of conservation of mass. Matter cannot be created or destroyed. It's just moved from one place to another. Things don't vanish. Things don't come in from thin air. All right, so there are four main types of radiation. There's more than this, but we'll address that in other courses. There is alpha radiation. There is, there is alpha radiation. There is beta radiation. There's a positron emission and gamma radiation, which is the most harmful. So this is the least harmful, and this is the most. Okay? So when you have an alpha particle that is emitted, it's relatively easy to protect yourself because all that's really happening is that you end up having a helium nucleus. Yeah, helium, like birthday balloons, coming out at you. Now remember, this number on the left-hand corner is the mass number, which tells you the number of protons and neutrons, like we learned in the last chapter. And this number down here is the atomic number. So this will tell you the number of the atom. That's right here. So you will definitely need your periodic tables because if you don't know what this is, you don't know what that is, and vice versa. Okay? It has a 2+ charge. There are no electrons in an alpha particle. Okay? A beta particle is going to be a negatively charged particle that has the mass less than a proton and a neutron. So in essence, you can see that this is sometimes written this way, kind of as like electrons being emitted. So you're going to see a negative charge. And that's exactly what a Geiger counter does, is it measures the charge of the air around something. Okay, a positron is a positively charged beta particle. Okay, so you're going to see that it is not the mass of a proton or neutron, but you're going to see that it has a positive charge of 1+. And then gamma radiation is so small that you don't really see anything here or there, so there is no charge, but it really is a damaging type of radiation. The reactions that we're going to do are not really going to cover our gamma rays, okay? But it will have these substances right here. All right, so alpha radiation is what we saw Ernest Rutherford using in his experiments with that gold foil. It's a particle that's literally equivalent to a helium atom. So you can see it written like so, He2 with the 4, or you can see it if you want to be fancy, write it with the alpha particle. And this is the lowercase Greek letter alpha. Okay, so an alpha decay example will still always obey the law of conservation of mass. Okay, meaning that the top mass numbers will all equal one another and the bottom mass numbers, or the bottom atomic numbers, will always equal the same on each side. Okay, so here we have polonium-210 going to decay into 206 and an alpha particle. So that's saying 210 is equal to 206 plus 4. Kind of obvious math, right? And then the atomic numbers that are written down here, okay, 84 tells you it's polonium. That's going to be equal to 82 plus 2. So 82 plus 2. If you don't know what element 82 is, you just look on the periodic table, you see there's lead, and then you see your helium atom right there. So the goal is to obey this law of conservation of mass and matter and get your top numbers and your bottom numbers to equal one another. The yield sign acts like an equal sign, all right, but we don't use yield signs in chemical reactions. A beta particle example will look like this. Okay, you can split, what is this right here, this lowercase n? Do you remember? This is a neutron. Okay, you can split a neutron into a proton and a beta particle. Okay, so 1 equals 1 plus 0. And then down in the bottom, 0 equals 1 plus negative 1. Let's take another look at that. 0 equals 1 plus negative 1. 1 minus 1 is 0. Look at that. There you go. Okay? Carbon 14. Yes, that's what we use for radioactive dating. Okay? Carbon 14 is equal to 14 plus 0. And 6 is equal to 7 plus negative 1. So again, 6 is equal to 7 plus negative 1. It's the same as saying 7 minus 1 equals 6. Okay, a positron emission means that you are emitting. Emitting means to give off a positron, okay, that positively charged beta particle. So here again, a proton can give off or can split up into a neutron and a positron. And here you can walk your numbers through. 1 equals 1 plus 0. And then for the bottom, 1 equals 0 plus 1. And this positive 1 means that it's going to be our beta particle, our positron particle. Okay, down at the bottom, you'll see something similar. You have your potassium 38 equals 38 plus 0. And then we have 19, which means it's potassium, decay into 18, which is argon, plus a positive 1, which is your positron. Okay, now if we capture radiation, this is going to be fusion, nuclear fusion. It means that we are going to add to one product. So here we have our electron. We're going to capture that with our proton. And if you think about it, an electron plus a proton will yield a neutron. A positively charged and negatively charged thing cancel each other out and make a neutron. This is the opposite of a beta emission. Look at that. So here we go. So if we follow the numbers, 0 plus 1 equals 1. And then negative 1 plus 1 equals 0. Negative 1 plus 1 equals 0. Okay? 106 plus 0 equals 106. And then down at the bottom, 47 plus negative 1 equals 46. 47 plus negative 1 equals 46. And who's 46? That's palladium. Who's 47? That's silver. Good thing you know those element names, huh? So like I said, alpha particles are relatively safe, okay? Alpha particles, you are protected by paper. I mean, that's all you need is a paper hat. Your clothes will be plenty protective. They're really big in mass. There's, the 4 He 2, it's the helium atom, so you can protect yourself that way. A beta particle, on the other hand, is a lot smaller, so it can fit through paper, but it would be protected by wood. And then lastly, we end up having our gamma particles, which are so small that they can go through the wood and the paper and end up have to be stopped by concrete. And they actually use a gamma ray gun to test the structural integrity after an earthquake or natural disaster, to see if there are any types of cracks. And, you know, if there are cracks somewhere in there, the gamma particles could go through, and they have like a detector on the other end, and that's how they measure that everything is safe. All right, so let's do 2 last examples and then set you on your way. So what does uranium-238 make if it undergoes an alpha radiation decay? So here we have uranium-238, and then you would look on your periodic table and find out that uranium is number 92, and then it's going to undergo a decay. So here's your alpha decay. What are you going to make over here? Well, law of conservation of mass. 238 equals 4 plus 234. 92 equals 2 plus 90. So who is element 90? Look on the periodic table. Thorium. Yes, the Asgardian. All right, that's where you are going to get thorium 234. It undergoes that alpha particle decay. All right, another example. Okay, complete the following reaction. What type of decay has occurred? All right, follow the numbers. 105 equals what plus 105? 0. 46 equals what plus 47? Well, that's a -1. What's that -1 particle called? That is a beta. Okay, so this is going to break up into a beta decay and your silver atoms. And that's what we have over here. This is a beta decay, and it can also be written like so. Okay, so if you forget the fancy beta, that's okay. You can also have it as the E, the electron, in there. Okay, so that is your nuclear reactions. Don't overthink it. It really is that easy.